Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Go to Morgan, to our friends in the Netherlands. Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Today is Friday, June 5th, 2026, and honestly, I am just so glad it is Friday. I desperately need the weekend.
Rough week. I mean, I can kind of see it in your eyes.
You have literally no idea. Okay, so I spent, I want to say 3 hours yesterday just fighting with a tiny, totally undocumented cable to fix my home Wi-Fi.
Oh no, let me guess, trying to get a main router to talk to a satellite node.
Exactly. I had the app open on my phone. I read the manuals twice. On paper, I was fully compliant with every single instruction the manufacturer gave me.
But the network still wouldn't connect.
Dead in the water, nothing. I ended up sitting on the floor, absolutely losing my mind, until I dug up some obscure Reddit thread from like 3 years ago.
Those are always the lifesavers, right?
Seriously. And it turns out there is a proprietary interface cable you need to bridge these two specific hardware versions. It wasn't in the manual at all. The manufacturer just assumed you would know. Yeah, it was incredibly annoying. But it actually got me thinking, imagine that exact same missing interface, that same messy lack of documentation, except it's hiding inside the braking system of a 2-ton vehicle doing 70 on the highway.
Yeah, the stakes change just a tiny bit when the hardware is moving that fast. But you know, the devil is always in the interfaces.
Right. And if you've ever wondered how ransomware and industrial control systems actually works under the hood, today is your day.
Yeah.
Because we have a massive deep dive lined up.
We really do. The source stack is heavy today.
It is. We are pulling from the Automotive SPICE guidelines, the ISSA 214304 standards, UNES Regulation 155, plus some incredibly sobering industry threat reports from Azure Technologies, Kaspersky, and Vicone.
It's dense material, but it is so critical for anyone paying attention to the industry right now.
Exactly. So let's set the mission for today's deep dive. We're going to dissect the hidden, highly vulnerable reality of automotive cybersecurity.
Right, from the ground up.
Yeah, going from the dirty factory floors where they build the parts, all the way up to the cloud servers managing the fleets. Because as we'll see, the biggest, most catastrophic risks don't actually hide in the raw code. They hide in the paperwork.
They absolutely do. Because building a car today, I mean, it isn't like building a car 30 years ago.
No, not at all.
You aren't just bolting stamped metal together on an assembly line in Detroit anymore. You are integrating dozens of complex technology stacks from, frankly, dozens of different companies all over the globe.
Okay, let's unpack this. Because calling modern vehicles cars almost feels inaccurate at this point.
It really does.
If you are driving a vehicle built after, say, 2018, you are likely sitting inside a rolling, highly hackable data center.
That is exactly what they are. I mean, a modern car contains hundreds of electronic control units, ECUs.
Yeah.
To really grasp this, you have to stop thinking of a car as one single unified machine. You have to think of it as a corporate office network on wheels.
So just a bunch of tiny computers networked together.
Exactly. You have hundreds of these microcontrollers, the ECUs, and they run everything. There is an ECU for your engine timing, one for the anti-lock brakes.
One for the climate control.
Right, one for the seat warmers, one for the windshield wipers.
Just like computers in an office, they have to actually talk to each other to get anything done.
Precisely. They communicate over internal networks using protocols like CAN, LAN, and automotive Ethernet. But, and what's fascinating here is, and also terrifying, frankly, protocols like the CAN bus natively lack any form of security.
I read that in the Azure Technologies report. But you have to help me understand the why here. Like, why would engineers build a network for a car and just, forget security?
Well, it wasn't forgotten. It just wasn't necessary at the time. You have to look at the historical context.
Yeah.
The CAN bus, the controller area network, was designed in the 1980s by Bosch. Back then, cars were getting heavier and way more expensive because every single physical switch needed a dedicated copper wire running all the way to the device it controlled.
So a wire from the dashboard all the way to the taillight.
Exactly. The primary goal of CAN was simply to reduce the sheer weight and cost of all that copper wiring. It allowed microcontrollers to broadcast messages on a single shared wire without needing a massive central host computer.
That makes sense. It was a brilliant, elegant engineering solution for 1986.
Right, but 1986 didn't have Wi-Fi.
Yeah, exactly.
The CAN bus operates on a broadcast system where there is zero sender authentication. Imagine an intercom system in an office building where anyone can pick up a microphone, shout an order, and everyone else just blindly obeys it.
Because they assume if you are in the building, you belong there.
Precisely.
Okay, wait, so if I am an ECU on the CAN bus and I just shout, hit the brakes, the brakes just do it. They don't check my ID or ask for a password.
They absolutely do not. If you are on the bus, you are trusted. Period. In the 80s, the only way to get quote-unquote on the bus was to physically break the car window, rip open the dashboard, and splice copper wires together.
So the security perimeter was just the physical locked car door.
Right. It was a physical barrier, not a digital one.
But today, that perimeter is totally gone. The attack surface has just exploded. We've got telematics, infotainment systems, V2X.
Let's define V2X for a second for the audience. That's vehicle to everything communication.
Right. The car talking to the outside world.
Yeah, your car talking to a smart traffic light to optimize traffic flow, or talking to the car in front of it to coordinate adaptive cruise control.
And of course, over-the-air or OTA update systems, so the car is constantly connected.
And that connectivity is exactly the bridge an attacker needs. I mean, the watershed moment for the industry, the one that proved this wasn't just some theoretical lab exercise, was the 2015 Jeep Cherokee hack.
Oh man, I remember that making massive headlines.
Yeah, security researchers Charlie Miller and Chris Valasek were able to remotely compromise the vehicle while a journalist was actually driving it down the highway.
Okay, this is where I need to know the how. Because it led to what, 1.4 million vehicles being recalled?
Something like that, yeah. A massive recall.
But how did they actually jump from the radio to the brakes? It's not like the FM dial is physically wired to the brake pedal.
No, but the digital architecture allowed it. Here is how it worked under the hood. The Jeep's infotainment system, the touchscreen unit in the dash, had a cellular connection provided by Sprint.
Okay, for like weather updates and streaming music.
Right. And the researchers found a vulnerability that let them dial into that specific cellular IP address from miles away. And from there, they rewrote the firmware of the chip running the entertainment system.
So now they own the radio. But again, the radio isn't the brakes.
True. But the infotainment system was wired into an internal network that touched a gateway ECU.
A gateway.
Think of the gateway ECU like a toll booth. It sits between the fun network, the radio, the Bluetooth, and the critical network, which is the CAN bus.
Oh, I see.
The toll booth is supposed to say, hey, radio, you can ask the CAN bus about the steering wheel volume buttons, but you absolutely cannot send steering commands.
Let me guess. They compromised the toll booth?
They bypassed it entirely. They found a vulnerability in a secondary microchip within the radio unit itself that was directly connected to the CAN bus.
No way.
Yeah. They reprogrammed that chip, effectively giving themselves a VIP pass right past the toll booth. And once they were on the CAN bus, remember what we said earlier?
No ID checks. They just grabbed the intercom and shouted, cut the transmission.
Exactly. And the car obeyed. They turned on the windshield wipers, blasted the radio, killed the transmission, and messed with the brakes, literally from their couch.
It's like, imagine the car's internal network is a medieval castle, right? The physical walls are incredibly thick. But the architects just decided to build a massive, wide-open, unmonitored secret tunnel straight from the castle courtyard to the local tavern.
That is a very accurate analogy.
And the tavern is just the infotainment system.
Right. The tavern is full of strangers, and the tunnel leads right to the throne room. And if we connect this to the bigger picture today, the threat isn't just the car itself anymore.
No.
No. It is the supporting infrastructure around the car.
You're talking about the EV charging stations.
Yes. The EV charging networks are expanding rapidly globally. And from a cybersecurity perspective, they are essentially unmonitored public endpoints just sitting on the street.
Because when you plug a modern EV into a smart charger, power isn't the only thing flowing. data flows too.
Exactly. They perform a digital handshake. They exchange billing data, state of charge information, vehicle identifiers.
So a compromised charging station, it's not just about getting free electricity.
Not at all. An attacker could compromise a charging station to manipulate your billing data or steal user credentials. But the real nightmare scenario, they use the charging station as a vector to inject malware directly into the car's systems during that digital handshake.
Wow. So the car thinks it's just paying for electricity, but it's actually downloading a backdoor.
Precisely.
Taking a breath here, because the long-term risk of this is what really gets me.
It should, because a poorly written piece of code in an over-the-air update server might not cause a crash today, but it creates a persistent backdoor. Think about how software updates work. The car is programmed to blindly trust updates signed by the manufacturer's server.
Command and control.
Yes. If an attacker can compromise the OTA infrastructure or spoof the command and control server, the CNC server, they aren't just hacking one Jeep on the highway anymore.
They are pushing malicious firmware to an entire fleet simultaneously.
It is an existential threat. If someone bricks 500,000 vehicles overnight, that automaker might literally not survive the week.
And that actually brings us to a completely different but equally terrifying front, the factory floor. Because the ransomware threat isn't just waiting out there on the highway or at the charging station, it is actively hunting the assembly lines right now.
This is the convergence of ICT and OT.
Okay, let's break those acronyms down for everyone.
Sure. ICT is information and communication technology. That's your standard enterprise IT, the back office stuff.
Payroll servers, email clients, HR databases.
Exactly. Accounting software. Now, OT is operational technology. These are the programmable logic controllers, the PLCs, that tell the massive robotic arms on the assembly line exactly how much torque to apply to a chassis bolt.
Wait, hold on. I'm going to push back here. That doesn't make any sense.
Right.
Why is the payroll system even remotely connected to the robotic arms on the assembly line?
Right.
Shouldn't there be an air gap? I mean, a physical disconnect between the office Wi-Fi and the heavy machinery.
You would think so, and 10 years ago there usually was. But here is where the relentless pursuit of corporate efficiency creates a massive blind spot. The business wants data.
Always.
The ERP system, the enterprise resource planning software, wants to know exactly how much raw steel to order for next Tuesday. And to know that, it needs real-time data from the factory floor about exactly how many chassis were completed today.
So they build a digital bridge between the dirty factory floor and the clean corporate office.
Exactly. They bridge the IT and OT networks. And the moment you do that, an email containing a malicious PDF opened by someone in the HR department can spill over and literally paralyze a robotic welding arm.
And the Kaspersky threat report was incredibly detailed on this. This isn't theoretical. We have real-world examples that are just devastating. Let's talk about August 2023. The Lockbit ransomware group hit Kendrion.
Right. Kendrion is a major Dutch manufacturer of electromagnetic parts for cars.
And the way the report describes it, Kendrion had to act drastically. They realized the ransomware was actively spreading through their network, so they entirely disabled their attacked business systems to prevent a massive data leak.
Which means they effectively had to blind themselves.
Yeah.
When you sever the IT systems to stop the spread, you lose visibility into your production pipeline. You halt operations just to save the data.
But the South Holland attack, that one really made my jaw drop. March 2023. They make commercial vehicle chassis components in Germany.
The timeline of that attack is a textbook example of IT to OT spillover. The attackers breached the IT infrastructure. SAF Holland detected the cyber attack and, as a containment measure, had to disconnect their global IT systems from the internet and shut down production sites.
Imagine the panic on that factory floor. Monitors suddenly going black. The robotic arms just physically stopping mid-motion.
Right.
And you can't even open the digital schematics on a tablet to try and fix them because the network is dead.
And the fallout was massive. The production downtime wasn't just a few hours. It lasted between 7 to 14 days, depending on the facility.
And the revenue loss, 40 million euros.
40 million euros,
Yeah.
just gone. Because a back office system got compromised. This is what happens when you have unsegmented networks. You think you are saving money on efficiency, but you are creating a single point of failure.
Okay, here's where it gets really interesting, and frankly a lot darker. If an attacker gets into the factory's IT network, and they can reach the systems controlling the production line, can they poison the well?
What do you mean?
Like, can they make the robots build vulnerabilities into the car.
Yes, that is exactly the nightmare scenario the intelligence reports warn about. Because ransomware, like extorting Saf Holland for millions, is loud. It's a smash and grab.
Right.
But the goal of a highly sophisticated state-sponsored actor wouldn't necessarily be loud.
They don't want the 40 million euros. They want the access.
Precisely. They would sit quietly in the R&D network or compromise the firmware compilation servers. Their goal would be to inject a subtle backdoor into the source code of an ECU before that component ever gets flashed onto the silicon.
Before it ever leaves the factory.
It is compromised at birth. And the operational risks for these manufacturers are so incredibly high because of their business model. The entire automotive manufacturing world relies on just-in-time supply chains.
Right. They don't have massive warehouses of spare parts sitting around.
Exactly. Parts arrive at the assembly plant hours before they are needed.
Incredibly tight production deadlines.
Exactly. Every single minute a factory is down costs millions of dollars. The attackers know this. They know that the OEM, the original equipment manufacturer like Toyota or Ford, will absolutely scream at the supplier and hit them with massive contractual penalties if the parts are late.
So the pressure is entirely on the supplier.
Yes. This makes the suppliers prime, highly motivated targets for extortion. The pressure to just pay the ransom quietly is immense.
Which perfectly illustrates why the technology isn't actually the hardest part of this puzzle. It's the humans. It's the organization.
Oh, absolutely.
Because we've talked about the physical hacks on the highway, the digital network breaches in the factories, but the documents we are looking at today highlight that the biggest, most dangerous gaps are organizational.
It's where compliance goes to die.
Yes, the CSIA, the Cybersecurity Interface Agreement.
I know, it sounds incredibly dry. It sounds like something a lawyer invented just to put engineers to sleep.
It really does.
But it is arguably the most critical document in the entire modern automotive supply chain.
Let's walk through how this actually works. Building a car requires an OEM, let's say Ford. Ford wants to build a new SUV. They don't build the braking system themselves.
Yeah.
They buy a complete integrated braking system from a tier 1 supplier like Bosch.
Right. And Bosch doesn't manufacture every single microchip inside that braking system. Bosch buys the raw silicon and the low-level firmware from a tier 2 supplier, maybe someone like NXP Semiconductors.
So you have this massive chain of custody for the code. And the CSIA is supposed to be the document that defines exactly who is responsible for the cybersecurity of that specific component at every single stage of its life.
But the reality on the ground, and this is quoted directly from the sources we analyze, is a total mess. The quote is, "On paper, the project was compliant. In practice, nobody had agreed the format or who owns what after SOP."
SOP meaning start of production.
Right, when the car actually starts rolling off the line.
To try and manage this chaos, the ISO 21434 standard uses something called a RASIC matrix, RASIC.
Let's break that down, because it's a great concept in theory. R is for responsible, the specific person or team who actually sits at a keyboard and does the work to secure the component.
Okay.
A is for approval, the manager who signs off on it and says, yes, this is secure. S is for support the team, providing the testing tools or the database. I is for inform the people who just need an email update saying the work is done. And C is for customer.
So they try to map every single work product, every threat assessment, every penetration test directly to this matrix.
That's the goal.
Wait, no, that's not right. The matrix implies people actually follow it.
True.
Reading these reports, it sounds exactly like a terrible group project in high school. You know the one where you have to do a presentation and nobody talks to each other all weekend?
Oh, I know the one.
The Monday morning rolls around, the presentation completely fails, and everyone immediately points fingers at everyone else.
Except in this case, the presentation is a 2-ton vehicle doing 70 miles per hour on the interstate.
Yeah, slightly higher stakes.
But that is a very apt comparison. Because the ultimate, most uncomfortable question in the automotive industry right now is this. 3, 5, 10 years after the start of production, when a critical zero-day vulnerability is suddenly found in a braking ECU, who pays for the patch?
Right. The car is already on the road. It's been in someone's driveway for 5 years. The OEM, Ford, gets an alert about the vulnerability. They expect a patch plan immediately. So the OEM calls the tier 1 supplier, Bosch, and says, fix this.
And Bosch looks at the problem and says, well, the vulnerability is in the microchip firmware. We didn't write that. So Bosch calls the tier 2 supplier and says, we need mitigation evidence and a firmware patch.
And the tier 2 supplier looked at their original 5-year-old contract and says, continuous monitoring and long-term software support were never in the commercial scope. You paid us for the chip in 2021. We aren't working on that code anymore. If you want a patch, you need to pay us a massive consulting fee.
And technically, every single engineer in that chain understands the vulnerability. They know exactly how to fix it.
But contractually, nobody wants to own the cost of deploying the fix.
This raises an important question about how we view security as an industry. The greatest vulnerabilities are not hidden in the threat analysis and risk assessment.
Because the engineers are usually pretty good at finding the technical flaws.
They are. The real vulnerabilities are hidden in the contractual interfaces between these companies. It is a governance failure, not a technical one.
So what does this all mean when we compare it to how cars used to be built? Because it's not like the auto industry is new to safety. We've had rigorous physical safety standards for decades. Why is cybersecurity so different?
It means we have to radically shift our mindset, which brings us to the fundamental conflict between functional safety and cybersecurity.
In the standards world, this is the battle between ISO 26262 and ISO 21434.
Exactly. ISO 26262 is the absolute Bible for functional safety. Its entire philosophy is about preventing hardware or software from accidentally failing.
Like wear and tear.
Yes. If a copper wire degrades over 10 years or a bit flips in a memory bank due to cosmic radiation, the system should fail safely. If the power steering motor dies, the driver should still be able to physically muscle the steering wheel. It is highly predictable physics and statistics.
Accidental failure. Mother Nature, bad luck.
Yes. Cybersecurity under ISO 21434 is entirely different. It is about preventing intentional, intelligent manipulation.
Deliberate malice.
Right. You cannot write a finite test suite for deliberate, creative human malice the way you can for a decaying brake pad.
Right, because a brake pad doesn't wake up and decide to invent a new way to brake.
Exactly. Testing a physical brake pad is a mechanical craft. You put it on a machine, you spin it, you wear it down, you measure the friction coefficient until it breaks. Testing for security is less of a craft and more an art form.
Because the target is moving.
You are trying to outthink a global network of highly motivated, incredibly creative hackers who are actively changing their tactics every single day.
Though there is some overlap, right? Like a secure car is inherently a safer car.
There is absolutely overlap. Think about a feature like Secure Boot.
How'd that work?
Secure Boot is a protocol that ensures only cryptographically verified software is allowed to run on an ECU when the car turns on. It checks the digital signature of the code. If a hacker tampers with the code, the signature breaks and the ECU refuses to boot.
That's cybersecurity?
Right. But Secure Boot also protects against accidental data corruption. If a memory chip degrades and the code gets scrambled by accident, the signature also breaks, preventing the car from running corrupted, dangerous software. That's functional safety.
What about the internal network monitors?
Same thing. Intrusion detection systems on the CAN bus can spot a cyber attack like a flood of fake steering commands, but they can also spot a malfunctioning broken sensor that is just spamming the network with garbage data because a wire got pinched.
But the economic realities here are just brutal. I was reading the comments on Bruce Schneier's blog that were included in our source material, and the commenters really hit the nail on the head. The auto industry relies heavily on agile updates, constantly pushing software patches over the air, because there is literally no economic incentive to secure things perfectly from the start.
It costs too much time and money to delay a car's launch by a year just to perfect the code. They want to ship the hardware and fix the software later.
And this creates massive technical debt. Look at what they call restricted devices.
This is a massive problem. A restricted device is exactly what it sounds like. It might be a smart meter on the power grid or an older, cheaper ECU controlling a car window. They are highly restricted in terms of physical memory, processing power, and battery life.
So you can't just slap modern encryption on them. I can't just push an OTA update to make my 2018 door lock secure against a 2026 hacker.
Exactly. The Schneier discussion pointed out a terrifying mathematical reality. If you want to use modern, quantum-resistant cryptographic keys, the kind of security we will need in the next decade to defend against advanced computing those digital keys might be 1 megabyte in size.
That sounds small for a laptop.
But a restricted device, like an older ECU, might literally only have 16 kilobytes of total memory for its entire operating system.
Wow.
You physically cannot fit a 1 megabyte key into a 16 kilobyte memory chip. It's like trying to park a semi-truck in a bicycle rack. It physically cannot be updated to modern security standards. The hardware is a dead end.
It's so cynical. These manufacturers are totally incentivized to harvest all our telemetry and driving data, where we brake, how fast we drive, where we go to sell to insurance companies and data brokers for pennies. But the second you ask them to bear the cost of supporting a 10-year-old software stack or replacing a restricted device, they balk.
And what happens when a Tier 2 supplier goes bankrupt? Let's say the company that made the infotainment system in your 5-year-old car goes out of business. Their servers shut down, their engineers go get other jobs.
Right.
Suddenly, you have aging cars driving around as unsupported Orkin tech. There is no PKI infrastructure.
PKI, public key infrastructure, the digital passport system that issues the secure certificates for the car to talk to the server.
Exactly. The digital passport office burns down, no PKI, no more updates, no vulnerability patches. The cars are just sitting ducks. This exact scenario is why the United Nations literally stepped in.
Really? The UN?
Yes. UNES Regulation 155 mandates that OEMs must utilize a CSMS, a cybersecurity management system. They can't just sell a car and walk away anymore. They are legally on the hook to prove they have the processes to manage these risks continuously long after the car is sold.
Okay, so this sounds completely bleak. The cars are fundamentally vulnerable because of old protocols like CAN. The factories are getting ransomed and shut down. The supply chain contracts are a finger-pointing mess. And old hardware physically can't run new security. How is the industry actually fighting back? Are they just giving up?
No, they're fighting back aggressively. They're fighting back with rigorous testing methodologies and by throwing cutting-edge technology at the problem. To achieve compliance with standards like ISO 21434, suppliers and OEMs have to prove, with documentation, that they are actively hunting for flaws in their own products.
Which means pen testing, penetration testing.
Yes. They hire ethical hackers to try and break in.
Yeah.
You have black box testing, where the testers know absolutely nothing about the system. They're just handed a finished ECU and told, break this, simulating a hacker attacking from the outside.
Okay.
Then you have white box testing, where the testers are given all the source code, all the engineering schematics, and told to find the logical flaws inside.
And gray box testing, which is somewhere in between.
Right. Gray box simulates an insider threat. What if the attacker has a stolen password? Or what if a supplier's network is already compromised? What damage can they do from partial access?
And then there is fuzz testing, which I absolutely love. It's such a beautifully chaotic concept.
It really is. Explain how you see fuzz testing.
To me, it's like letting a toddler bash a piano keyboard with a hammer until a string snaps, just to see which string is the weakest, so you know which one to reinforce.
That is surprisingly accurate. In a digital sense, fuzz testing is basically bombarding the communication stacks, the CAN bus, the LIN network, the automotive Ethernet, the Bluetooth receiver, with massive amounts of invalid, randomized, malformed data.
You aren't sending real commands. You aren't saying turn on the radio.
No, you are sending a million variations of random characters at lightning speed. You are just screaming ductile noise at the ECU's processor to see if you can force a memory leak, a system crash, or a panic state.
Why do you want it to crash?
Because if an attacker can crash the ECU by sending it garbage data, they might be able to exploit that crash to inject their own code during the reboot process.
Okay, so you fuzz it to find the weak spots, you pen test it to see if someone can break in, and then you put active defenses inside the car to catch whatever slips through, right? The IDS and IPS.
Intrusion detection systems and intrusion prevention systems.
Yeah.
Yes. These are software agents that sit directly on the vehicle's internal network, actively monitoring for anomalies. Let's go back to our castle analogy. If the infotainment system is the tavern, the IPS is the heavily armed guard standing at the secret tunnel.
Right. So if the infotainment system suddenly tries to send a command to the steering column, which it should absolutely never do under normal circumstances, the IPS guard says, wait a minute, you don't have the authorization for that, blocks the command, and flags the anomaly.
Exactly. But flagging the anomaly creates a massive, entirely new problem for the automaker.
The logs. The petabytes of logs.
The logs. Think about it. Millions of cars on the road, all generating telemetry and security logs every single second. Every time a Bluetooth connection fails, every time a sensor blips, a line of code is written to a log file and sent back to the OEM servers.
Right. And the ECU source material specifically highlights this initiative, AH 2025 PS04. It's an AI and machine learning lifeline for these engineers. Because if you have a mountain of logs that big human engineers physically cannot read it all. It would take centuries.
What's fascinating here is that the integration of AI into log analysis isn't just a neat trick or some Silicon Valley buzzword to satisfy investors. It is a desperate mathematical necessity. The manual analysis of unstructured, noisy log files is incredibly slow and highly prone to human error.
You're looking for a needle in a haystack of needles.
Precisely. By the time a human engineer sifts through a petabyte of logs, finds the subtle pattern of a slow-moving intrusion and traces it back to its root cause, it's too late. The fleet is already compromised, the hackers are already in.
So they use AI as the ultimate bouncer. The AI parses the massive logs, automates the defect detection, and actually translates it. It extracts the root causes in natural language.
Yeah, that's the key.
So instead of an engineer staring at a million lines of hexadecimal code, the AI just tells him, hey, this specific Bluetooth stack on this specific SUV model is actively being probed by an unknown MU's address.
Automation is the only way to scale defense against automated attacks. Hackers are using automated scripts to probe millions of IP addresses a minute.
Yeah.
You have to fight automation with automation. And this vigilance has to be maintained throughout the vehicle's entire life cycle.
Not just while it's under warranty.
Right. UNIS R155 and ISSA 21434 demand that this security posture stretches from the initial concept drawing on an engineer's whiteboard all the way to decommissioning and end of support when the car finally goes to the scrapyard and the memory banks are wiped.
It is a monumental task. When you really step back and look at it, we are asking an industry that spent a century mastering mechanical engineering, bending steel, thermodynamics, combustion, to suddenly master global, distributed cryptographic software defense overnight.
And the stakes couldn't be higher, which actually raises a chilling thought that keeps a lot of security researchers awake at night if we project this forward.
Oh, good. I definitely needed some more anxiety for my Friday afternoon. Let's hear it.
We've talked extensively about the struggle to maintain and secure these vehicles today, right now, with companies that are actively in business. But what happens 15 years from now? Imagine the year 2041.
Yeah, I'm picturing it.
There will be millions of smart, highly connected cars still on the road. Cars built in 2024 by massive corporations, but also by smaller EV startups that may have gone completely defunct a decade prior.
The orphan tech we mentioned earlier.
Exactly. Permanently unpatchable vehicles. Their restricted devices are totally obsolete. Their security certificates have expired. They are full of well-documented public vulnerabilities that any amateur script kiddie can download off a dark web forum in 30 seconds.
And they are still driving down the highway at 70 miles an hour.
Yes. And because of that, we aren't just looking at the risk of individual tragic accidents. We are looking at the potential for a massive, high-speed, 2-ton botnet.
A botnet of cars.
Yeah. Imagine a coordinated attack where a hacker weaponizes 100,000 unpatched cars simultaneously, not to ransom the drivers, but to gridlock a major city's infrastructure during an emergency. They can be weaponized at scale.
Well, that is a truly terrifying image to end the week on. The idea of zombie cars gridlocking a city because a company went out of business in 2030.
I think I'm going to walk home today, stick to the sidewalks.
Yeah, honestly, I think I'll join you. My Wi-Fi router issues suddenly seem very, very small.
Yeah.
That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons. See you in the next chapter.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared. Stay critical. And keep following the evidence.